Okay, next up is question 9, and part A says, prove that if the sum of a sub n, as n goes from 0 to infinity, is a convergent series, then the limit as n approaches infinity of a sub n is equal to 0. And we're given a hint. It says, use the fact that a sub n is equal to s sub n minus s sub n minus 1, where s sub n is the nth partial sum of the series. Okay, so to start, first going to write out the claim that we're seeking to prove. Okay, it says that if the sum of a sub n, as n goes from 0 to infinity, is convergent, then our job is to show that a sub n approaches 0 as we let n approach infinity. Okay, so to start the proof, since we're assuming this series converges, then by definition that's saying that the limit of the sequence of partial sums, so this limit here of s sub n as n approaches infinity, exists. And I'll go ahead and give that limit a name. I'll call it L. Alright, so now note that if I write out the partial sum s sub n, so that's where we just sum up all the terms up until we get to a sub n, and then write out the partial sum s sub n minus 1, again, sum up all the terms until you get to a sub n minus 1 there, and then take the difference of those partial sums. On the right-hand side, everything drops out except for a sub n, and so we get that a sub n is equal to s sub n minus s sub n minus 1. Okay, it's the difference between these two consecutive partial sums, and that's really what we're seeing here in the hint. Okay, so now the idea is to take the limit as we let n approach infinity, and here we're seeing, well, for this difference, since we're assuming that s sub n converges to L, if you think back to our discussion of recurrence relations in sections 9.1 and 9.2, if s sub n is converging to L, s sub n minus 1 must also converge to L. Okay, because if we're converging to L, right, that means that the s sub n's are clustering around L. And see, s sub n minus 1, that's just the term that immediately precedes s sub n. So if s sub n's clustering around L, so is s sub n minus 1. And so to finish now the proof, okay, since these two terms are approaching L themselves, their difference will approach L minus L, which is equal to 0. And that concludes the proof. Again, we've shown that if this series of a sub n converges, then a sub n must approach 0. All right, great. So now for part B, I want to go over a few things related to what are known as conditional statements, also known as if-then statements, and then we'll tackle what we're supposed to do here in part B. But so what is a conditional statement? Well, notationally I can write this as A, and then this is an implication symbol, so A implies B. You can also read this as if A is true, then B is true. Okay, so as an example of this, let's say A is the statement, I punch the wall, and B is the statement, my hand hurts. Okay, then the conditional statement would be, well, if I punch the wall, then my hand hurts. All right, so next thing I want to highlight here with regards to conditional statements is that the following two statements are logically equivalent. So the statement A implies B is logically equivalent to this statement. Now this little symbol you see in front of the B and the A, okay, we read this as the negation of B and the negation of A. So you can also say not B and not A. So what this statement right here is saying is that if B is false, then A is false. And what I'm saying here is that these two statements are logically equivalent, right? So if A, then B is equivalent to if not B, then not A. Okay, this is what's known as the contrapositive of the conditional statement A implies B. Now, as you can see, there's a lot of symbolic logic going on here. You likely have not taken a class in symbolic logic. If you're thinking about going into math, then absolutely do so. It'll make, you'll probably be required to anyways, but it certainly makes a lot of things simpler. But so going back to our example, if I punch the wall, then my hand hurts. Okay, what I'm saying here is that that statement is equivalent to the following. Okay, if my hand does not hurt, right, so that would be the negation of B, then I did not punch the wall. Okay, that is the negation of A. So these two statements are logically equivalent. So what does all of this have to do with part B? Well, part B says, show that if the limit of A sub n as n approaches infinity is not 0, then the series of A sub n must diverge. Okay, so how do we do that? Well, what we showed in part A, right, was that if this series of A sub n converges, then the limit of A sub n is equal to 0, right? So here's our statement A implies this statement B. Okay, so what I'm saying up here is that A implies B is logically equivalent to not B implies not A. So what does the contrapositive look like here? Well, not B, right? What's the negation of this? It'd be that the limit of A sub n is not 0, meaning, well, A sub n could converge to some non-zero number, or maybe this limit doesn't even exist. But what we're saying there is that the limit of A sub n is just not 0, okay? That then must imply, well, not A. What's the negation of the series converging? It'd be that the series diverges. So what the contrapositive here is saying is that the limit as n approaches infinity of A sub n not being 0 implies the series diverges. Okay, and so in other words, part A, all the work we did there, immediately implies the result in part B just from appealing to the fact that any conditional statement is logically equivalent to its contrapositive. All right, so to summarize, a lot going on here. But in summary, okay, we have two key results that we're going to refer to down the line. Okay, the first, this is part A, says that if you know that a series converges, then it must be the case that A sub n approaches 0 as n approaches infinity. Okay, now the equivalent statement is that if A sub n does not approach 0, so again, whether A sub n approaches maybe some non-zero value or this limit just doesn't even exist, then we can conclude that the corresponding series here of A sub n diverges. Now this result here is what is known as the test for divergence, and we will see this quite a bit in the next couple sections. Okay, so a little bit of a preview of things to come. Okay, now the one thing I want to end here with is a rather important warning, okay, and it says the following. It says, if all we know is that the limit of A sub n as n approaches infinity is equal to 0, we cannot conclude whether or not the series of A sub n converges. We need to do more work to determine this, okay? So you got to be really careful when it comes to the logical implications here, okay? So notice this first statement. It says, if we know the series converges, then A sub n approaches 0. So if I punch the wall, then my hand hurts. Okay? But you got to be really careful. It's tempting to want to say, okay, let's say my hand hurts, right? In other words, all I know is that A sub n approaches 0. Can I conclude that I had to have punched the wall? Well, no, not necessarily. I could have punched the wall, but I also could just have my hand hurting from some other reason. Okay? Same thing here, right? Just if all I knew was that A sub n approaches 0, it may or may not be the case that this series converges. And we'll see examples in the next few videos here where A sub n approaches 0 and the series converges. But there's other examples where A sub n approaches 0 and the series diverges. You have to be very, very careful here when it comes to the logical implications. All right, well, that's a good place to stop, and we will pick up on all of this with the next video. Thanks so much.